Yeah, it's great to be back here at KITP at this CERI conference with my CERI colleagues, and it's exciting to hear so many exciting developments. And but today I'm wearing a slightly different hat. I'm going to tell you about the connection between the Accelerator Frontier and the CERI. And I think the connection is obvious, right? So the CERI, we make CERI advances to address a lot of fundamental questions in nature. And at the same time, I think we all agree that physics is experimental science, and big accelerator facility that has been, and I think it will continue to be front and center for any of the future advances. They're testing CERI ideas, make discoveries that leads to new series. So I think this is a figure that you probably are familiar with. This is a time, and this is the center of mass energy. We have many successful examples. On each one of them, we have something that memorable that happened that advanced the field a lot. And for that, of course, it's important to consider new accelerator designs and consider whether they are feasible or not, and consider their cost and so on and so forth. And this is where the accelerator frontier comes in. Right, so I think the connection is very obvious. So this is just a layout of the accelerator frontier. I won't go through all the charts, but there are 7 different working groups and working on different aspects of accelerators. And there's also a sort of overarching implementation task force. We'll look at a bunch of all the accelerator proposals and so on. I'll talk more about what they are doing later. And within the CERI frontier, there are also quite a number of related ROIs for white papers, and they focus on collider phenomenology, EFT, and model building, and sorry, for precision theoretical techniques for precision physics. At the same time, the focus here and the CERI frontier, I think very well justified, are the theoretical techniques. Okay, and so I'm going to focus more on the connection between, in particular, between the CERI and the future colliders. And on this topic, I think there is not a really dedicated discussion in and organized by the CERI frontier. And as Laura already mentioned, there are more such a discussion happening in the energy frontier. At the same time, I think a future collider has been a big focus for many theorists. So there's really not a lack of participation from the CERI community. And there are lots of these activities. I think Laura mentioned some of them. These are a set of agoras that discussing like the different kind of colliders, and there's also a series of muon collider conferences organized by the Muon Collider Forum, for example. And all these activities has been have a lot of participation and the contribution from the CERI community. So what the theorists can contribute is to look at give you the first looks and estimates and the phenomenological studies of the physics cases. A lot of these examples are already available as a part of for example, the European strategy update and the various conceptual design reports and the technical design reports for various collider proposals. And also again, I would say the recent part of this Snowmass process, this established the Muon Collider Forum also generates a lot of new interest and studies for muon colliders, high energy muon colliders. And there are still areas more studies needs to happen, such as photon collider or EP collider. So for the rest of my talk, I'm going to give you a review about the rough, very high level review of what kind of collider options have been proposed so far on the table. And I will give you a very brief summary of physics case people have talked about so far. and mostly because I think you're sort of familiar with this already, and to actually delve into each one of those really takes a conference on its own. Okay, so first, collider proposals. So this is a list of proposals that are compiled by the implementation task force within an Accelerator Frontier. I think the actual proposal and also parameters keep changing. I think because of lack of focus, you cannot see here anyway, see very clear anyways. But you know, this may not be the final list, and it may not be the final parameters, but this is at least covers most of them. They fall into different classes. There is this class of low energy lepton colliders, and they are mostly aimed at becoming Higgs and Z factories. And many of them also have a interesting physics output on the WW threshold and TT bar threshold. Okay, so these are either linear colliders running at the low energy or circular E plus E minus colliders. Also, there's a muon collider Higgs factory proposal. Then there is this class of high energy lepton colliders, also photon colliders. They, you know, depends on the proposal. There goes from going from ILC to C3 and click, and to a set of muon collider proposals, also photon collider proposals, and the Wakefield accelerators. These are going from they covers quite a broad range, but basically they covers the multi-TeV to tens of TeV range. Okay, so this is the. And then there is also a set of proposals for high energy circular PP colliders. And there, again, the numbers has been changing a little bit. And for example, I know SPPC has been updating their benchmark central mass energy numbers, but roughly speaking, they are focusing on 100-ish TeV range. You know, unless you really wanted to take seriously that we are going to use the whole Mexican Gulf as a, you know, there's this so-called collider at the sea proposal. Anyways, yeah, I think Laura already showed this table. This is a set of benchmark that the Energy Frontier compiled. It's largely the same as the one that I showed on the previous slide, but this does show you also different colliders has a different running modes, like going from, for example, ILC has can go from the Higgs factory mode to a much higher energy mode, and so on. So and there's also a list of hadron colliders with different energies, and then also muon colliders. Okay, so it basically contains roughly the same information. Okay, and there has been a discussion. A lot of the activity in Accelerator Frontier is focusing on looking at each of these proposals to, you know, from various angles and study their feasibility, the cost, the all kinds of impact. Okay, so I'm going to just show you an example of a table that they will present, and they haven't filled in the blanks yet, but these are the list of low energy E plus E minus colliders, and these are their main running mode and the luminosity. But there are some columns, proposed columns to be here, that is years to, for example, from construction to actual data, and there's a cost column, and there is a, you know, a power consumption column. Okay, so this is I think as far as I understand from my accelerator colleagues, this is not just taking from the proposal that people submitted to Snowmass, but this will add their own judgment to it. Okay, so this table, there may be even more columns. There has been discussions to add like 1 or 2 more columns on this table, and I think this kind of table will contain a lot of information. Okay, so all right, so now the next, I will just very briefly summarize the kind of physics case people have been put forward so far. And so yes, so colliders, we basically wanted to go to smaller distance. We find different ways, either go there directly or study their virtual effect and so on. We wanted to go to smaller distances, right? So here is the history again, and we are going forward. I think recently there has been a small workshop at Slack focusing on talking about future colliders, and the Tao made the point that everything has a factory, and the Higgs needs one too. Okay, so that's the one-line justification for why we need to go forward. I think we all agree, but at the same time, I think it's also useful to lay out more about the physics questions we would like these facilities to address. So this is where theorists can contribute a lot and has contributed a lot. And in the past years, several main physics drivers has been identified. And one of them is the Higgs, the other one is dark matter. Okay, in Higgs is surrounding the Higgs coupling precision measurement, but also the question about the naturalness that Raman talked about yesterday. And also the dark matter, in this case, there's a huge landscape of what possible dark matter can be, as Yonis mentioned. But as far as the physics driver, for the high energy collider point of view, the physics driver here is really the testing WIMP models. Okay. And there are also a very rich physics program associated with all these proposals, and you can search for portals to dark sector, flavor physics, testing QCD, and so on. Okay, but in case you wonder, there's no guarantee, of course, to discover new particles at any of these things. But I think the main justification is that we will learn a lot, no matter what. Okay, so let me just briefly show you, flash to you some slides about the Higgs physics. And this is the Higgs coupling measurement as projections at some future colliders. This is mostly Higgs factory. This is an estimate for the muon collider. And the basic message here is that a per mil measurement is possible. And this is 1 order of magnitude, roughly 1 order of magnitude better than what LHC can do. And here are some basic messages, right? So the Higgs factory's precision very roughly scales with the number of Higgs, scale with statistics of Higgs boson. And these are the low energy Higgs factory and the high energy colliders tends to be sensitive to different kind of couplings. And also measurement at the lepton collider are more model independent. They can give you, sorry. Okay, yeah. They give you a model independent mass measurement of width and the CH coupling. And also Z factory can also be very useful to, for electrical precision measurement and also feed into the overall precision measurement program. And this is a measurement of the Higgs self-coupling, frequently mentioned as another main physics driver for the Higgs coupling measurement. And you see that we really need a high energy lepton collider or high energy PP collider to really nail this coupling down to a percentage level. And a frequently mentioned physics question that this kind of measurement can address is to understand the nature of electric phase transition, which is sensitive to the shape of Higgs potential, which is sensitive to the size of the Higgs self-coupling, right? So whether it's a second order or whether it's first order, and you see that with a combination of different Higgs measurements, such as Higgs Z measurement and the Higgs self-coupling measurement, one can really cover a lot of the model space. Okay, so this is just an example of a singlet model. And for naturalness, we really wanted to look for the new physics that are associated with it. I think Rama mentioned that yesterday. And there, we really wanted to go to higher energies for directly going after the new physics like that. And roughly speaking, hadron collider you will reach about 10% of the central mass energy of the Hadron Collider. So if you have 100 TeV, Hadron Collider, you roughly reach to 10 TeV. And for Lepton Collider, you roughly reach to half of the central mass energy. Okay, so this is the, yeah, so this is the muon collider. For example, high energy muon collider reach. Okay, dark matter. Yeah, again, so the main benchmark for the future colliders are the so-called simple WIMP models, where the WIMP is a part of the electric weak multiplet. There's a neutral member of the electric multiplet, and they are good dark matter candidates, and these are very predictive benchmarks in the sense that their interactions with standard model are all gauge interactions. Okay, so there are very few free parameters in this in this setup, in addition to its mass. Okay, to fully test this kind of paradigm for hadron colliders, 100 TeV goes some ways to test some candidates, but ideally, if you wanted to really go all the way, test all of them, you really wanted to have an even higher energy proton collider. And for muon collider, yeah, this may not be the most updated figure, and but the rough message is that we probably need a muon collider up to 30 TeV to fully test all these models, because searching for WIMPs are actually WIMP particles. The signals actually are quite difficult. It's not as straightforward. Okay, so here is another. I'll end before I end. I wanted to just mention, another example of the kind of a serial input that we can give, right? So often we think about the colliders mostly in terms of energy reach, but it's important that at least for collider design, right, the needed luminosity is also a very important parameter. So really the luminosity has to be based on physics need. So these are just a few benchmarks. So for example, here are the either fermionic or scalar top partners, the kind of energy and the luminosity you would need to reach to, for example, roughly half of the central mass energy that you reach of the goal of the fullest reach of a collider. These are these curves. And you can also ask what is luminosity you need if you wanted to make an EFT measurement where the cutoff is 3 or 10 times the central mass energy. These are these green curves. This is the kind of luminosity you need. And you can also say, if I wanted to have a vibrant, a good Higgs program, right? So at least you probably wanted to have 1 million Higgs, but maybe you want more. These are these two curves. Okay, so it's just, again, very rough summary of a physics output of a kind of collider that you can have. And I can, this is a somewhat old plot. I probably should. We're trying to make updated ones. And these are some of the collider proposals so far. So they are all excellent. Some of aiming at the Higgs program, they are doing a good job. Having more luminosity than needed, and so on. Okay, so. But I think the way that you look at this is one of the questions one could ask is that, if one is really difficult to get up to the full proposed luminosity immediately, is starting with some lower luminosity still worthwhile, just as an initial stage? Okay, I think the answer is probably yes. We can still do quite a bit of physics, even with a somewhat lower luminosity. Eventually, of course, you wanted to get up to there to do good Higgs physics and all kinds of search for dark matter and so on. Okay, so let me just also say that I've been focusing on the question of future colliders. I haven't, but there are also other activities going on in the AF, such as the accelerator needed for the neutrino physics. There's also a interesting connection between this and the muon collider proposals. Also, the accelerator for physics beyond collider, physics programs looking for dark sector, sphere process, and so on. I hope the talk from other frontiers will cover some of this. Okay, let me just conclude. Yeah, so looking forward, I think theorists have been and will continue to be at the forefront of high energy physics. So we identify questions, we suggest solutions, we propose ways to testing ideas, right? This kind of activity will exactly lay the foundation for the planning of future collider physics. And as I think Michael already emphasized, that the future is at stake, right? Our next step is at stake. I think we all have to think harder. You know, beyond everything has been said and done, is there anything big we have missed, for example? Okay, thank you.
Real quick, we continue to fall further behind.
We've got a hand from Marcella and Ronnie, so maybe I'll start with Marcella.
Oh, hello. Yeah, just one comment, Lian-Tao. Very nice talk. I was thinking when you think about how to present issues related with Higgs and dark matter. For the Higgs, you mentioned precision measurements and naturalness. I think, of course, we have a very nice talk this morning about from Raman, but I could make my point much stronger related to finding other Higgses, which you mentioned in relation with phase transition, but very tangentially. And I think that it's an argument that, first of all, is, I think personally, is very exciting, but also is an argument that we can push forward in the sense that it is kind of expectable to believe that maybe there are other scalars around there, which are for us necessary in so many scenarios that we theorists think about. But also just, you know, it is very relatable to say, you know, we have found these Higgs, we are trying to understand all its properties the best we can, and we need to understand if there are others of its kind, other Higgs cousins. So I would put more emphasis on that, and then, I mean, I'm sure there is, but just a comment that jumps up to me, that would be very good to concentrate on the idea of building or looking for a high luminosity LHC and for future colliders with the idea that other Higgs particles are expected to be there.
Yeah, so I completely agree. So I think, you know, well, let me not say too much more. I think, you know, a lot of the studies, I mean, I'm sure you're aware of, have a lot of the studies with extra Higgs as well. And I agree with you that we should emphasize, definitely emphasize more on these aspects.
Thank you.
We also have a hand from Roni, although Roni, if we can ask you to be quick, otherwise you'll be in trouble with Pedro.
I can handle Pedro, don't worry. Just to complement Lian-Tao, at the end you mentioned accelerators for neutrinos and for low energy physics. So and you correctly, and this is the most important burning further future question of the high energy accelerators for high energy frontier. So just to complement and inform that, since this is about theory informing other frontiers, there has been an exercise with very strong theory involvement to inform the low energy accelerator designed for neutrinos and accelerator designed for rare processes at Fermilab. So there will be a white paper associated with that, and many theorists, Stefania, Gordon, myself, Maxime Pospelov have been involved in that. So there's more theory involvement in these other frontiers that you circled. Thanks. On to Pedro.
Thank you. I completely agree. I think again, I hope there will be talks also from other frontiers in this workshop. I hope they will mention some of the activities here as well.
Okay, so let's thank Lian-Tao.
Okay, thank you.